Yeah, g'day mate, how are you? Today we're doing traits, alright? Today we're talking about traits, and more than once in my time running Rust training for engineering teams, people have found my accent a little confusing, especially with that word. So I just wanted to make that one clear up front. A trait is an interface. It specifies the methods a type must implement if it has that trait. For example, this is the display trait from the standard library, and it requires one method with exactly this name, these parameters, and this return type. This trait is used anytime you format a string with an empty pair of curly braces as the placeholder. So long as X is of a type that implements the display trait, I can use println to print it out, or I can use the format macro to construct a string. Some types implement the display trait and some don't. To write a generic function or a generic type that can work with any type T as long as it has the display trait, I can use trait bounds. T:display means exactly that. It puts bounds around the set of types that are allowed for T. This basic concept is extremely useful. We've already talked a bit about the copy trait and the clone trait representing the ability to duplicate values. There's also the send trait, which says it's safe to send this value to another thread. And there's the sync trait, which says it's safe to access the value concurrently from multiple threads. The Iterator trait is for types that can produce a sequence of items you can loop over. The add trait is for adding values together using the plus operator. And I could go on. There are many, many traits. This is a rich aspect of Rust, the language, and the ecosystem. At rustcurious.com you'll find this map that I call the elements of Rust. The top half shows all the types built into the language, and in this video series so far we've worked our way through the major pieces of the type system. Now it's time to scroll down to the second page, which maps out the traits that are built into the language. In this video, we'll look in detail at some important traits. Understanding these will really unlock how much of the standard library you can make sense of. For example, if you have a hash map and you want to look up an item by its key, there's this nice friendly get method. And holy generic type parameters, Batman, there's a lot going on here. People complain about fighting with the borrow checker, but I think half the time they're actually fighting with the trait solver.
Map error exists, but its method trait bounds were not satisfied.
So, I'll show you how to read stuff like this. I'll also show you how to make your own traits, your own interfaces that let you do so much more with generics. Along the way, we'll talk about trait inheritance, traits with associated types, generic traits, and something called the Orphan rules that control which types you're allowed to implement traits on. But apart from all that, there's not much to talk about. Oh, and I have a practice exercise for you. Wait, no, actually, I have three. There are three practice exercises ranging from quite easy to a little more challenging. Should be fun. There are so many interesting, useful traits that I want to show you, more than we can possibly cover today. So the focus of this video is to give you a solid understanding of the trait system to set you up for your own exploration. Curious? Imagine that we have a database that contains items of different types, like videos, channels, and so on. We're building a management interface for this database, and in the UI we have logic that should be shared across all these item types. For example, to show any item in the UI, we need a label string to describe it. So let's create a trait that represents the interface that must be provided by all item types. I declare a trait called item, and this says to be an item you must implement a method called label that takes a shared reference to self and returns a string. This looks just like the declaration of a method, but there's no function body, just a semicolon. This trait is public, so it can be implemented by types in other modules and other crates. I don't have to put the pub keyword on the method declaration because the details of a trait are automatically visible to anyone who can see the trait. One of our item types is a struct that represents a video, and it has a title string. To implement the item trait for this video type, we write impl item for video. This is called a trait impl block. Inside the block, we have to write the method just like it's declared in the trait. But of course, this time we have to provide the method body. We have to return a string, so let's use the format macro to build a string that makes it clear this is a video with the title. We can do the same thing for the channel type. A channel has a name and a number of subscribers. And we want to include both those details in the label, so this time when we implement item for channel, we write a different method body. It includes the channel name with an @ symbol and the number of subscribers in brackets. The fact that a type implements a trait is always public to anyone who can see that type and that trait. There's no such thing as privately implementing a trait, but if you really want to, you can implement a trait on a private type and then wrap that in a public type. So now we have a trait that represents the capabilities that are required for all item types. Any item must be able to produce a label string, even though the code it uses to do that varies between different item types. So now we can write some shared logic that can be reused across all item types. This function describes an item. Inside the angle brackets, we declare a generic type parameter t, so this is a generic function. t:item means this function works with any type t as long as it implements the item trait. It takes a shared reference to the item, &t. And inside the body of the function, we know that t has the item trait, so we can call the label method on it. Let's put this to use. So if we create a video struct, we can call describe with a shared reference to the video. That prints out item is video traits. And if we have a channel, we can call describe with a shared reference to the channel. That prints out item is channel at Rust Curious with a modest number of subs. So that's the basic idea. A trait defines an interface, types can provide their own implementations, and we can use the trait as an abstraction over all those types. There's something fun we can add to this example. Let's say we want to store integers as items. I don't have to create a new struct to hold an integer, I can just implement the item trait for an existing type. So I can say impl item for i64, and in the body of the label method I say it's an integer and the value is just self. That means I can call the describe function with a reference to an integer. And yes, taking a reference to a literal is perfectly valid. And if that wasn't strange enough, I can now call the label method on any i64. So I can call 10.label and this returns a string. Cool, right? That sound you can hear is some people's heads exploding. In many languages, there's a distinction between primitive types and class types, and the mechanism for defining an interface can only be used with class types. In Rust, traits are more orthogonal to types, if I can put it that way. You can implement your trait for any type you want. Now, there are some limitations to this. First, you can only call the label method using dot syntax if the item trait is in the current scope. This is for disambiguation, so it's explicit which trait the method is coming from. If you need to be explicit at the call site, you can name the trait and call the method inside that namespace, passing the self argument explicitly. So this is equivalent to calling 10.label. The other limitation is on which types you can implement traits on, and this depends on the crates in which the types and traits are defined. A crate is a compilation unit in Rust. It's either a library or an executable. Now, I'm going to explain what's called the Orphan rule, and the purpose of the rule is that for a given type and a given trait, there can only ever be at most one implementation of that trait for that type. It's not possible to have multiple implementations. It's never ambiguous. And to explain this rule, I need the help of a rabbit. This is my friend Bunny. I've known Bunny for a really long time. Sadly, he's missing his tail. It was pulled off by Peter Schultz in 2nd grade. So if you're out there, Peter. Now, I have my crate, and any types or traits I define in my crate are my types and my traits. Bunny has his crate with his types and his traits, and you have your crate with your types and your traits, okay? Okay, good. So, the rule is as follows. To implement a trait for a type, either the trait must be yours or the type must be yours. Or they can both be yours, that's fine. So I can implement my trait for any type. My types, your types, Bunny's types, primitive types like i64, any type, because it's my trait. You can implement your trait for anybody's types. Bunny can implement his own traits for anybody's types. You can only implement my trait for your own types. If you define a type in your crate, then you can implement anybody's traits on it, that's fine. What you can't do is implement my traits on Bunny's types. And the reason is, if that was allowed, then someone else could do the same thing. And then there would be two conflicting implementations of my trait on Bunny's type. So, Bunny, you don't have to worry about that happening, okay? Okay, good. All right. Okay, thank you for your help. Yep, thank you. Okay, yes, good. Okay. Thank you. Yep. Okay, thank you. Okay. So that's the basic idea of the Orphan rule. That's why we can implement the item trait for i64. And the rule also lets us implement traits from other crates on our own types. Let's take a look at two traits from the standard library. Display and debug are both used for formatting values into text, and they correspond to different placeholders that you'd use with println or the format macro that builds a string. When you use an empty pair of curly braces as a placeholder, that uses the display trait to format the value. The intended purpose of the display trait is to produce output that will be visible to end users of an application. If you write a placeholder with :?, it uses the debug trait to format the value. The purpose of the debug trait is to produce output that will be visible to developers, somebody debugging the application. The two traits look identical, they work the same, but they're used for different purposes. Only some types are intended to be displayed to users, but it's very common for types to implement debug, because that's useful for us developers in log messages, panic messages, etc. And a single type can implement both, but produce different output for display versus debug. Both traits require this format method, which takes a mutable reference to a formatter. That's the thing you write the output to, and it might end up feeding those characters to standard output, or store them in a string, or write them to a file, or a socket, or a panic message, who knows. It returns a result because performing I/O might run into an error. Let's implement the display trait for our channel type. So impl display for channel. And in the body of the format method, I could call various methods on the formatter object, f, but it's much easier to just use the write macro to do it for us. Write is just like println, it takes a format string with some arguments, but it also takes a destination as its first argument, and we can use the formatter, f, as that destination. There's no semicolon at the end of the line because the write macro returns exactly the result type we need. If writing to the formatter produces an error, it'll be in the result we return. So this is how we implement display, and we can format that output however we want. We could do the same thing to implement debug, but there's a much easier way because the compiler can do it for us. If we go back to the definition of the channel struct and add the derive attribute to it, then the compiler will add an automatic implementation of the debug trait. Only certain traits can be derived this way. You can enable this for your own custom traits, but it requires writing a procedural macro or proc macro, which is a whole other thing. Now if we print out a channel with the display format, the placeholder with empty curly braces, then we get the @ symbol and the number of subs in brackets. If we print it out using the debug format with :?, then the automatically derived implementation spits out the name of the struct with curly braces and a comma-separated list of the fields with their values. And those values are also formatted using the debug trait. So this is super handy. You can just slap a derive debug on all your types, and that makes it easy to use them in panic messages, log messages, etc. One place you might not want to just derive debug is on encryption keys, passwords, stuff you don't want accidentally turning up in log files. There's a logging crate called log, and it provides macros for writing log messages at each of the various levels of catastrophe: info, warning, error, fatal, etc. They use the same formatting machinery as println, so you can write a log message using the info macro with a debug placeholder. Let's say I want to add some logging to my describe function. And remember, this function takes a reference to an item of type t, which must implement the item trait. So if I try to log that item with debug formatting, will this compile? No, we get an error, t doesn't implement std format debug. And the error message helpfully points at the placeholder in the format string. Then it points at the declaration of the describe function, and it suggests consider further restricting type parameter t with trait debug. And it shows us the syntax for doing that with t:"item plus std format debug. So let's do that, and I'm going to make it slightly tidier by importing the debug trait into our namespace with use std format debug. Now in the angle brackets I can say t:"item plus debug, and now the function compiles. We know that whatever type t is, it must have the item trait and the debug trait. If you think of each trait as a set of types, then this is taking the intersection of those types. So we only accept types that have both traits. The stuff in the angle brackets is starting to get a little bit long here, so we might prefer to use an alternative syntax with something called a where clause. The where clause goes just before the function body. So now in the angle brackets, we just declare the type parameter t, and then in the where clause, we write the trait bounds t:"item plus debug. It's conventional to write the where keyword on a line on its own because you can have many conditions, and those are normally written with one condition per line, separated by commas. So we could actually split this condition into two, with t:"item and t:"debug as separate conditions. This is equivalent, it's just a style choice, but later we'll see some conditions that can only be written in a where clause. They can't be written inside the angle brackets because the thing on the left of the colon is not a generic type parameter, it's what's called an associated type. Before we get to that, there's something bothering me about the design we have right now. The item trait defines the label method that kind of does the same thing as the display trait. Display is intended for user-visible output, and it's more flexible than this label method that only knows how to construct a string. Display can be used to construct a string, but it can also write directly to a stream without allocating a temporary string object. Also, there's some repetition here. We have this consistent pattern in the label with a word on the front to say what kind of item it is, followed by a colon and then the stuff specific to that instance. It would be nice to remove that repetition, to have one place in the code to describe that pattern. And maybe it would be useful to expose the string describing the kind of item as a separate thing in case we need to format it differently in some other part of the UI. So I'm going to redesign the item trait so that it requires the display trait. To do that, we need trait inheritance. In C++, structs and classes can inherit from other structs or classes. You can have a class hierarchy with a base class and derived classes, and then you get to worry about things like multiple inheritance and the diamond problem and virtual base classes and all that stuff. In Rust, we don't have those problems because structs cannot inherit from other structs. The only option is to use composition to make a struct that contains another struct. What we do have in Rust is interface inheritance, and in Rust interfaces are called traits, so we call this trait inheritance. So now in the definition of the trait I've added item:"display, meaning the item trait inherits the display trait. That means any type that implements item must also implement display. We don't need the label method anymore because the implementation of the display trait will output the title of the video or the name of the channel and the number of subscribers. Instead, we have a new function called kind, which returns a string describing what kind of item this is, so video or channel, etc. And notice this function does not take self, so you don't need an instance to call it, you just need the type. And the string it returns is &tick static str, which we call a static string slice. All string literals have this type. So now to implement the item trait for video, the kind function just returns the string video, and for channel it returns channel. And of course we also need to implement display for each of these types, just like I showed you earlier. But what about the label method? We've already written so much code that depends on it, like the describe function. Well, we can keep the label method and we can provide a default implementation for it in the trait definition. Anytime a trait provides a function body, that's just a default, and a type implementing the trait can override that default if it wants to, but that's optional. This default label method formats the string just like before. It calls the kind function on the self type. Self with a capital S is an alias for the type we are implementing. And for the part after the colon, we know we can format self with the display placeholder because we inherit the display trait. We require any type implementing item to also implement display. This code inside the trait definition is generic code. Self with a capital S is a generic type parameter that gets substituted with whichever type implements this trait. So now we have a much better separation of concerns. This label method is reused by default across the various types. This is the one place that says the format of a label contains the kind of item followed by a colon and then the display representation of that item. Our existing describe function still works fine because the item trait provides the label method. We do still need t:"item plus debug because we use the debug representation in the log message. What if we had lots of functions that take an item and log it? They'd all need to say t:"item plus debug, and that could get tedious. We could instead decide that all item types must implement debug. If we make that part of the item trait, then we wouldn't need the plus debug everywhere. So, in the definition of the trait, we can just say item : display plus debug. This means to implement item, you must also implement display and debug. Item now inherits multiple traits, and that's fine. If you have multiple inheritance PTSD from C++, don't worry. There's no problem here because traits are just interfaces. They don't say anything about the layout of objects. And if you've never heard of the diamond problem with multiple inheritance, good. Keep on living your life. You're not missing anything. Okay, so we've seen how a trait can define the functions that are required for an interface. The item trait says, as well as implementing display and debug, you have to provide a kind function. And optionally, you can override the default label method. Sometimes, some of the types involved in the interface will depend on the type implementing the trait. For that, traits can specify associated types. As a quick warm-up for associated types, let's first take a look at type aliases with the type keyword. When I say type myInt equals i64, myInt is just a new name for i64. This does exactly what typedef does in C. It just creates a new name for an existing type. And I can assign an i64 value directly to a variable of type myInt because it's the same type, just a different name. Okay, now let's use that in a trait. This is the Iterator trait from the standard library. It represents the concept of iterating through a sequence of items, one step at a time. Anytime you use a for loop, you are using an iterator that implements this trait. And to be an iterator, to implement this trait, you have to do at least these two things. You have to say what your item type is, and you have to provide this next method that returns the next item in the sequence, if there is one. The next method takes a mutable reference to self because the job of the iterator is to keep track of where we are up to in the sequence. When you call next, it has to take a step forward and update its internal state to remember that. It returns an option because that's how you can tell when you're at the end of the sequence. You keep calling next and you get some item, some item, some item until you reach the end, and then you get back none. The type inside the option is self : item, which is how we refer to the associated type that we defined above. Remember, self with a capital S is an alias for the type implementing the trait, so self : item is the type associated with that implementation. Okay, let's make our own iterator. This one's going to iterate over a range of integers, so I'm calling it intRange. Of course, you've already seen the built-in range type that can do the same thing, but that one is generic, which makes it a bit more complicated. Let's keep things simple here. So intRange has two fields, start and end, and they're both integers. When a type is an iterator, the state it holds represents the items that have not yet been visited in the iteration. So when I use this intRange as an iterator, at each step I'm going to increment the start value until it reaches the end. The values between start and end are really the remaining values that we haven't visited yet. So now we can implement the iterator trait for intRange. We have to do two things. We have to say what our item type is. This iterator will produce integers, so we say type item equals i64. And we have to provide the implementation of the next method. And as I said, the intRange represents the range of values we have not yet visited. So if start is less than end, then I increment start and return some integer. Otherwise, we've reached the end and I return none. By the way, it doesn't matter here whether I'm returning option i64 or option self item. Those are equivalent. Item is just an alias for i64 at this point. Now, because I've implemented iterator, I can use intRange with a for loop. I create a range with a start value and an end value, and then I say for x in range. Whatever I put after the in keyword has to be an iterator, or actually something that can be turned into an iterator. I'm skipping over that tangent because I want to focus on the associated type, the item type. The for loop is going to take this iterator, range in this case, and hold on to it. It's the iterator that keeps track of where we are up to. So each time around the loop, it calls the next method. And if next returns an option with some item, then that item value gets assigned to the pattern on the left of the in keyword, in this case the variable x. And its type is the item type that we declared when we implemented the iterator trait. So the type of x will be i64. Whoever implements the trait gets to choose that type. In this example, the range is the iterator. It's a range of integers, so the items are integers. If you're iterating over a collection like a vec or a hash map, then the situation might be very different. Typically, the iterator is a separate object that has a reference to the collection, along with some way to track where it's up to. So each item is a reference to a value in the collection. An iterator that produces shared references to values will be a different type from an iterator that produces mutable references to values, and they'll have distinct item types. Vec has its iterator types, hashmap has its own iterator types, there are many iterator types. What's more, when you have an iterator, there are dozens of iterator adapter methods that will wrap it in a different kind of iterator. For example, the iterator trait provides the enumerate method. If I call range.enumerate, then I get a new iterator, and its item type is a tuple containing the current iteration count along with the item from the original range iterator. So now I'm destructuring that tuple with the pattern I, x, and I can print out the index I'm up to in the iteration along with the integer from the range. In the final practice exercise, you get to re-implement enumerate. I reckon re-implementing tiny little pieces of the standard library is a great way to learn how stuff works. I mentioned earlier that in a for loop, the thing on the right of the in keyword must be an iterator or something that can be turned into an iterator. Now that you know what an iterator is, let's come back to that. In this example, we have an array, and I say for x in a mutable reference to the array. This gives me an iterator that produces mutable references to the elements in the array, one at a time. So x is a mutable reference to an integer, and that's the item type of this iterator. So how does that work? Well, the expression on the right of the in keyword must have a type that implements another trait called IntoIterator. This trait represents the ability to be turned into an iterator. I'm showing you a slightly simplified version of the real trait, and what I want you to pay attention to is the associated type IntoIter. The trait only has one method. It takes self by value, and it returns a value of that IntoIter type. This is the iterator type that we have been turned into. The interesting part is that the declaration of the IntoIter type has a trait bound on it, which says it must implement iterator. So when you implement this trait, you can choose whatever type you like to return from this method, but it must be an iterator. Now, a minute ago, we created a type called intRange and used it with a for loop, but we didn't say anything about this IntoIterator trait. How did that work? Well, the standard library contains this. It says for any type I with the iterator trait, you get an implementation of IntoIterator on that type. And of course, I is already an iterator. It doesn't need to do anything, so it just returns self. Any type that implements the iterator trait automatically gets the IntoIterator trait as well. So now you know about the iterator trait and the IntoIterator trait. Those are both built into the language because for loops rely on them, so here they are. And now you also know about associated types and trait bounds on associated types. We're about to move on from iterators to talk about generic traits. I know there's more. But if you'd like to get a little bit of practice in first, you might like to pause the video now and have a go at this exercise. It's a simple one. You just take the stack we built in video number 7 and implement Iterator on it. There's a to-do comment at the bottom of the playground that tells you what to do. The idea is that the next method just calls pop, so iterating a stack will remove all the items from it one at a time, and those items are just chars. This is simple to do, but once you've got it working, have a read through the unit tests. They demonstrate a few of the provided adapter methods that come for free with the iterator trait. This exercise is an easy one to get your feet wet before we add any further complexity, so give it a go. Okay, moving on, generic traits. In video number 8, we saw how a generic function is really a family of functions, and a generic type is really a family of types. Well, the same thing works with traits, so a generic trait is really a family of traits. Take, for example, the mul trait. It represents the ability to be multiplied by something. This is the trait used by the multiply operator. It has a generic type parameter called RHS. That's the type on the right-hand side of the multiplication. And you can see why it makes sense for this to be a family of traits, because it might be possible to multiply a particular type by several different right-hand side types. This is the definition of the mul trait. Self is the value on the left of the multiply operator, and RHS is the value on the right. That's defined by the generic type parameter RHS. And actually inside those angle brackets it says RHS equals self, which just means that by default the right hand side is the same type as the left hand side. So if you implement the mul trait without specifying RHS, that's what you get. Or if you use mul as a trait bound without specifying RHS, same thing. Generic parameters don't have to provide a default, but this one does. We have an associated type called output, and you guessed it, that's the type of the output from the multiplication. So the mul method returns self output. This works just like the item type for iterators. And the question I always get is, why does the trait system need generic parameters and associated types? Like, why doesn't the iterator trait just use a generic type parameter for item instead of an associated type? There's an important distinction here, and it has to do with who gets to choose which types. With iterator, either you implement iterator or you don't. It's not a family of traits, it's one trait. If you do implement iterator, then you get to choose what item type you produce, and you write that in the impl block. When someone uses this thing in a loop, that's the item type they get. They don't get to choose. With multiplication, whoever puts your type on the left of the operator also gets to choose what type they put on the right-hand side. There might be several different right-hand side types you support, and you can provide for those by implementing several different members of the mul family of traits. The caller of the multiplication operation chooses the type on the right, and if you support that, you get to choose the output type. So, generic parameters are chosen by the client of the interface, and associated types are chosen by the implementer of the interface. Typically, generic parameters are for inputs and associated types are for outputs. So, let's see an example. Let's invent a type to represent a vector in two-dimensional space, so it has x and y coordinates. And there are a couple of different ways we can perform multiplication with vectors. If I multiply a vector by a scalar, then I get a bigger vector. But if I multiply a vector by another vector, we could define that to mean we calculate the dot product, which produces a scalar. So let's start with the dot product. We're multiplying a vector by a vector, so I say impl mul vect for vect, and the result will be a scalar, so we say the output type is f64. And this is how we calculate the dot product. Okay, that was easy, so now we can say v1 times v2, and we get a scalar. We also want to handle multiplying a vector by a scalar, which produces a new vector scaled by that amount. And remember, the right-hand side type is the generic parameter to the mul trait. So this time we say impl mul f64 for vect. Our output type will be vect, and to calculate the result, we just multiply each of the coordinates by the right-hand side. So now we can multiply a vector by a scalar, and we get a bigger vector. So now you can see how each of these impl blocks supports multiplication of a vect with a different type on the right-hand side, and we get to specify the type of the output in each case. Associated types for the win. Now this kind of multiplication should be commutative. I should be able to multiply a scalar by a vector and get the same result. But right now this doesn't compile. There is no definition for multiplying an f64 on the left with a vect on the right. Can we support that? Well, yeah, we just swap the types, right? So now we say impl mul vect for f64. The type on the left is the self type, f64, and the type on the right is vect, the generic argument, and this works. But wait a minute, what about the orphan rule? To implement a trait for a type, we said that either the trait or the type has to be defined in the current crate. The mul trait isn't mine, it's defined in the standard library. And f64 is definitely not mine, it's a built-in primitive type. So why does this compile? The answer is that because vect is defined in the current crate, mul with vect as the generic parameter is considered to be sufficiently mine that this is okay. Mul is generic, so it's really a family of traits, and I'm responsible for the members of that family that have my type, vect, in the angle brackets. The exact details of the orphan rule are interesting to look up, but basically it just works. Mostly you can just forget about it and implement the traits you need. And as with so many things in Rust, if you get it wrong, the compiler will let you know. Okay, we've had a good look at the mul trait for multiplication, and that's pretty much how all the operator traits work. We have arithmetic operators for addition, subtraction, multiplication, division, remainder, and these are all generic because they all have a type parameter for the thing on the right-hand side of the operator. The exception is neg for negation, which is not generic because it's a unary operator. There is no second argument to deal with. Same goes for the bitwise operator traits, AND, OR, XOR, shift left, shift right. These are all generic with a right-hand side type, and the NOT operator is unary, so it doesn't need one. To the left, we have the comparison operator traits that work the same way. The distinction between partial order and total order is basically there to accommodate types like floats with a nan value, not a number, which doesn't fit into a total order across all possible values. Same deal for the distinction between partial equivalence and equivalence, because nan is not equal to nan. Continuing to the left, we have the index and IndexMut traits, which are used anytime you index into a collection with square bracket syntax. Again, these are generic with a parameter for the type of the index inside the square brackets. And you get to implement this trait in the next practice exercise, so let's take a closer look. The idea is that a collection type will implement this trait so it can be indexed with square brackets. IDX is the generic parameter for the index type. We've already seen how an array can be indexed with a usize to access a single element, or it can be indexed with a range to access a slice of elements. Other collection types will support other index types. So for example, you can index into a hash map with a key. The type parameter for the index is called IDX, and the associated type for the data you get access to is called output. And there's an interesting trait bound on it that says output : sized. What the hell is that? Well, first, sized is a special built-in trait. We call it a marker trait because it doesn't specify any methods or associated types. If a type implements a marker trait, it means that type has some special property. So the copy trait is another marker trait that marks a type as being safe to copy. The sized trait means this type has a size that is known at compile time. Almost all types automatically get this trait. And in fact, anytime you write a generic type parameter or an associated type, by default it will only accept types that have the sized trait. The assumption is that you'll be passing this type around by value, and to hold a value in a variable, the compiler needs to know how many bytes it takes up. So the sized trait is the one implicit bound on all type parameters and associated types by default. You can relax that restriction by saying $sized. This means I accept any type, even types which do not have a fixed size. The ones with no fixed size are called the unsized types, and here they are: the unsized array slice, the unsized string slice, and the unsized trait object. These are the types you cannot hold directly by value in a variable because they don't have a fixed size at compile time, but you can have references to them. That's fine in this trait because the index method only returns a reference to the output. It never holds it by value. So for example, vec implements index with a range of usize, and it says the output type is the unsized array slice. The index method returns a shared reference to the output, which means it's returning a shared array slice. That's a pointer and a length. It has a fixed size, so this works fine. Okay, I am lying. If you go and look at the code for vec, you won't find exactly this. There's actually another trait involved as an abstraction across all the different range types, but this is what it boils down to. And in fact, this is what it used to be in Rust 1.0 before that abstraction was introduced. I think this example shows why it's so useful to have the unsized types as distinct things we can talk about in the type system, even though we can't hold them directly in variables. The implicit sized trait bound on generic types means we don't usually have to think about this, and we can opt out of that restriction when it's useful. Now, to be clear, $sized means maybe sized, maybe not. It works with all types, including the unsized ones. So vec also supports indexing with a usize, not a range. In that case, the output type is t, the element type of the vec, and the index method returns a shared reference to t. And again, I'm lying for the sake of clarity, but this is what it boils down to. In the practice exercise, you're going to implement something like this, but with the slab type from the generics video. But wait, there's more. The index trait only handles shared references. That means it's read-only. There's another trait called IndexMut for indexing with mutable references. IndexMut inherits the index trait, meaning it builds on top of the ability to index in a read-only way. It extends that by adding this IndexMut method, which takes a mutable reference to self and returns a mutable reference to the output. Notice this trait doesn't declare an associated type for output. It inherits that from the index trait, so the output type is always consistent whether you're using index or IndexMut. If I have a vec and I index into it using square brackets, if I'm just reading that value, then the compiler will use index using shared references. If I assign to that location, then it will use IndexMut. And notice that in both cases, what I'm accessing is the integer in the vec. So x is an integer, it's not a shared reference to an integer. And I can add the value 50 directly to the value I get mutable access to using IndexMut. The compiler uses the references as locations in memory to operate on, and the user doesn't have to explicitly dereference those references. If you want a reference to an element in a collection, then you can explicitly take a reference to it. Just like when you index beyond the end of an array, indexing into a collection using square brackets is intended to panic if the index is invalid. The trait methods don't return options, they return references, so if the method can't return a valid reference, it has to panic. And that's what we're going to do in this next practice exercise. It's at the same URL, rustcurious.com/9. Just scroll down a bit further until you find the right playground. This playground contains a solution to the Slab exercise from video number 8, so spoiler warning if you haven't done that one yet. Slab is a generic collection type, and each entry can either be vacant or occupied. When you insert an item, you get back a usize that's the index to the newly occupied entry. Your job is to implement the index and IndexMut traits so that items can be accessed using square bracket indexing. And you'll find some to-do comments to that effect at the bottom of the playground. The Slab already has methods called get and getMut that take an index and return an option with a reference to the item if that entry is occupied. I encourage using these, and you can just unwrap the option because it's expected to panic if the entry is vacant, meaning that index is invalid. That's what HashMap does, so we can do it too. There's not much code to write for this one. The point is to get some practice implementing traits on a generic type when you have a few different generic parameters and associated type to keep track of. Once you've got the declarations right, the code is pretty simple. Okay, and now for the third and final exercise. You're really getting your money's worth today, aren't you? Again, it's at the same URL, just keep scrolling down to find the playground button. In this exercise, you get to re-implement the Enumerate iterator adapter that we talked about earlier. This is one of the unit tests, and you can see that we have a function called Enumerate. It's a generic function, so it takes any iterator and it wraps it up in a new iterator type. The item type of the new iterator should be a tuple containing the iteration count as a usize and the item from the original underlying iterator. I've provided the bones for you. The struct enumerate has a generic parameter I for the underlying iterator and a usize for the iteration count. I've even written the enumerate function for you to initialize the struct. All you have to do is implement the iterator trait. At the bottom is a to-do comment with a reminder of what to do. The interesting part is really just getting the declarations right. Then there's a little bit of logic in the next method. Once you've got that working, if you still haven't had enough, there are 2 bonus challenges for you. Each one has an extra unit test for you to uncomment. Make sure you do them in order. The first one adds a method called sizeHint, and the second one uses that to implement a trait called exactSizeIterator. Okay, that's it for the exercises. If you get through this lot, then I reckon you're on your way to a pretty good understanding of the trait system. I love hearing how people go with the exercises, so please let me know. Before we wrap up, I just want to address something that came up last week. I learned that some people saw the 3D artwork for the channel and they were worried it might have been produced with AI tools. Some people avoided watching the videos for that reason. So, for the record, everything you see here is handcrafted. I have never used any AI tools to make these videos or the thumbnails or the animations. I make all the 3D renderings by hand in Blender. And can I just say, I really like this one. A 10-pin debug header and an HDMI display interface. That's just a fun way to think about traits. I enjoy coming up with these. When I started Rust Curious, I set out to make the highest quality video learning materials available for Rust. This is a high effort project for me. I'm hoping the eventual audience for this little channel might get a whole lot bigger than it is right now, but who knows. Over the coming videos you might see me experimenting with much simpler thumbnails, but please know this does not indicate any change in my commitment to producing quality material. It's a weird time to be on the internet, and I'm figuring out how to do this. Also, no judgment on the people who thought my stuff might be slop. We are all swimming in it. It's insidious. What can you do? If you like the stuff I'm making here, the best thing you can do to support the channel is to let people know. Maybe you know someone who might be a little Rust curious? Coming up will be some videos about the stack and borrowed references, and then lifetimes. Lifetimes are really glued onto the side of the generic system, so we now have everything we need to talk about them properly. So don't miss that one. Have fun with the exercises, stay curious, and I'll see you soon.